Welcome to General Chemistry Mini Lecture Series, Lecture 45, Molecular Geometry. Previously, we already learned that VSEPR theory can be used to predict molecular geometry. That is because electron pairs around a central atom arrange themselves so that they can be as far as possible for each other. And that results in different molecular geometry. Here, let's go over the steps for applying VSEPR theory to a molecule. Number one, draw a Lewis structure of the molecule. And number two, we need to classify each electron group as a single electron, non-bonding electron, or lone pair electron, single bond, double bond, triple bond. Then all of those count as one electron group or electron domain. After that classification, we can determine the total number of electron groups around the central atom. Use that total number of electron groups to determine the electron group geometry, or sometimes we call that electron domain geometry or fundamental geometry. If there are two electron groups, the electron group geometry is linear. 3 groups, trigonal planar. 4 groups, tetrahedral. 5 groups, trigonal bipyramidal, like this. And 6 electron groups, then we have octahedral. Those are electron group geometry, not molecular geometry yet. Then we can use the numbers of bonding and non-bonding electron groups and table 45-1 shown in the next slide to determine the molecular geometry as well as bond angles. This is a very useful table in determining electron geometry, molecular geometry, and bond angle. This shows the type of molecules. A means the central atom, X means the surrounding atoms, L means lone pairs. Let's start with AX2 molecule. There are 2 bonding groups, 0 lone pair. Therefore, the electron geometry is as same as the molecular geometry. Both are linear. The bond angle is 180 degrees, and those are the examples. For 3 electron groups, there can be 2 types of molecules. The first one is AX3, 1 central atom, 3 surrounding atoms. Therefore, the bonding group of electrons, 3, non-bonding or lone pair is 0. The electron geometry is trigonal planar, and then the molecular geometry is also trigonal planar. The bond angle is 120 degrees, and those are the examples. The other type of molecule with a total number of 3 electron groups is 2 surrounding atoms and 1 lone pair. Therefore, there are 2 bonding groups and 1 lone pair. Electron geometry is still trigonal planar because electron geometry is determined by the total number of electron groups. However, the molecular geometry is bent because there are only 2 surrounding atoms, not 3 like in this trigonal planar molecule. So the bond angle here is less than 120 degrees. The reason it's less than 120 degrees is because the lone pair electrons, they occupy more space, and that squeezes those 2 bonds a little bit toward each other. As a result of that, the bond angle is less than 120 degrees. And here are the examples with bent shape. Let's move to 4 electron groups. For AX4 molecules, 4 bonding groups, 0 lone pairs, the electron geometry and the molecular geometry both are tetrahedral. And the bond angle 109.5 degrees. Those are the examples. The second type of the molecule here is 3 surrounding atoms and 1 lone pair. So therefore, 3 bonding electron groups and 1 non-bonding electron group. The electron geometry is still tetrahedral, but the molecular geometry is trigonal pyramidal. The base of the pyramid is a triangle. That's why it's called trigonal pyramidal. Because that lone pair requires greater space, the bond angles in molecules with a trigonal pyramidal is less than 109.5 degrees. Here are the examples for this type of molecules. The last one in this category is molecules with 2 surrounding atoms and 2 lone pairs. The total number of electron groups still 4, but 2 bonding groups, 2 lone pairs. Electron geometry stays the same, tetrahedral. But now, instead of having 4 surrounding atoms, there are only 2 surrounding atoms. The other 2 are occupied by lone pairs. So therefore, this is bent structure. And the bond angle is less than 109.5 degrees. Water has a bent molecular geometry, and those are the other examples here. For molecules with a total of 5 electron groups, we have 4 different types. The first one is with 5 bonding groups, no lone pair. Therefore, the electron geometry and molecular geometry are the same. That is trigonal bipyramidal. So the base of the pyramid is a triangle, so therefore that's trigonal bipyramidal. There are 2 different bond angles. The first one is 90 degrees between the axial bonds and the equatorial bonds. Note that there are 2 axial positions, this one and this one. The other angle is 120 degrees, that's between the bonds in the equatorial positions. There are 3 atoms in the equatorial positions. 1, 2, 3. Those 3 atoms. That's molecules with 5 bonding groups and 0 lone pair. If there are 4 bonding groups and 1 lone pair, the electron geometry or fundamental geometry stays the same, which is trigonal bipyramidal. But the molecular geometry becomes seesaw. It is important to remember the lone pairs occupy the equatorial positions. Therefore, one of the 3 equatorial positions, 1, 2, 3 equatorial positions, is occupied by a lone pair, the molecular geometry is no longer trigonal bipyramidal because the molecular geometry is only concentrated on the atoms. And the lone pair here, there's no atom. So that's why this is seesaw. The bond angles, they are either less than 90 or less than 120 degrees. The reason for the slightly smaller bond angle is because this lone pair occupies a little bit more space than squeeze the other atoms a little bit together. If there are two lone pairs that leaves three bonding groups, electron geometry still trigonal bipyramidal, but after moving another surrounding atom, we have this T shape. That's why we call that T shape. The bond angle is just 90 degrees, and those are the examples for T-shaped molecules. If there are only two bonding groups and three lone pairs, which means all of the three equatorial positions are occupied by lone pair electrons, then the molecular shape, if we just focus on the atoms, is simply linear. And those are the examples for molecules with a linear shape. Last, let's go over the molecules with a total of 6 electron groups. If there are no lone pairs, the fundamental geometry and the molecular geometry are the same. Both are octahedral, and the bond angle is 90 degrees. Those are the examples. However, if there are 5 bonding groups and 1 lone pair, fundamental geometry still octahedral, then the molecular geometry becomes square pyramidal. Again, the lone pair always occupies the equatorial positions. There are 4 equatorial positions. In this case, you have 1 occupied by the lone pair, 2, 3, and 4. Those are the equatorial positions. Now let's focus on the molecular shape. As you can see, in this case, there's a pyramid, and the base of the pyramid is square. That's right here in this plane. So this is the base of the pyramid. It's a square. Of course, it does not look square with my drawing, but it is a square. A pyramid with a square base. Because this lone pair electrons occupy greater space, the bond angles are slightly less than 90 degrees. And those are the molecules with square pyramidal shape. Now let's take a look at molecules with 4 surrounding atoms and 2 lone pairs. In other words, 4 bonding electron groups, 2 non-bonding electron groups. Fundamental geometry is still octahedral, and then the molecular shape is just a square planar. Okay, you see this square. And the bond angle is 90 degrees. Those are the examples. How about molecules with 3 surrounding atoms and 3 lone pairs? The fundamental geometry or electron geometry is octahedral, but now the molecular shape is T-shape, and the bond angle is 90 degrees, and those are the examples. The last one, 2 surrounding atoms and 4 lone pairs, 2 bonding groups, 4 non-bonding groups. The fundamental geometry is still octahedral, but now all of the 4 equatorial positions are occupied by the lone pairs, the molecular shape is just linear and the bond angle is 180 degrees. And this is an example for molecules with a total of 6 electron grooves and a linear shape. There are different ways to depict molecular structures. Let's take example of carbon tetrachloride. The Lewis structure can be shown in these two ways, but the second depiction is better than the first one. The first one you may mistake the molecular geometry for carbon tetrachloride as a square planar, as it shows here, but that's incorrect. It is actually a tetrahedral. So therefore, this three-dimensional Lewis structure is a better depiction. Please note the carbon atom and these two chlorine atoms, along with the two single bonds, they are all on this projection plane, or they are all in the planar of your computer screen. But this chlorine atom, the one with this wedge that is in front of your computer screen, well, this dash one, that is behind it. So this gives you a sense of three-dimensional structure for carbon tetrachloride. Then there is the so-called ball stick models. So those balls are atoms and the sticks are bonds. Of course, for the molecule, in this case that's tetrahedral. So for the molecule shape, looks actually more like this, tetrahedral. But in reality, the carbon Cl bond, the other three, they are also chlorine atoms. The carbon-chlorine bond are never exposed to the outside of the carbon and chlorine atoms. So therefore, in reality, this is what we see. So therefore, this space filling model is the closest to the real molecules. Let's work on the first example in lecture 45. Determine the electron and molecular geometries for carbon tetrafluoride. So although we already learned that carbon tetrachloride is tetrahedral, but I want to show you how to determine that through those steps we already went over just a short while ago. Number one, we draw a Lewis structure of the molecule, and then let's classify the number of electron groups for the central atom. There are 4 bonding electron groups, or 4 single bonds, and there are no lone pairs on carbon. The total number of electron groups is 4. Therefore, the electron geometry is tetrahedral. Since we consider the bonding groups when determining molecular geometry, and there are 4 bonding groups, no lone pairs, therefore the molecular geometry is the same as the electron geometry. In this case, is tetrahedral. Let's work on the second example. We need to determine the electron and the molecular geometries for ammonia, NH3. Again, we follow those steps. So first write down the Lewis structure, and we know there are 3 single bonds and 1 lone pair. Therefore, the total number of electron groups is 3 plus 1 equals 4. Then the electron geometry is tetrahedral. Among the 4 electron groups, there are 3 bonding electron groups and 1 lone pair. So therefore, the molecular shape is not tetrahedral anymore. It is pyramidal. Similarly, let's work on the geometry for water molecule, H2O. There are 2 single bonds and 2 lone pairs. So therefore, the total number of electron groups is 4. Therefore, the electron geometry is still tetrahedral, the same as carbon tetrachloride and ammonia. But the molecular geometry is bent, because when we consider molecular geometry, we only consider those bonded atoms. We never consider lone pairs. That's why this bent structure. Therefore, water molecule has a bent structure. Let's take a look at the effect of lone pairs and bond angles. We actually already taught this a little bit in the previous few slides. Because the electron density of lone pairs is exclusively on the central atom rather than shared by 2 atoms like bonding groups, the lone pair requires more space on the central atom. That in turn affects the bond angles, making the bonding group angles smaller than expected. Let's take ammonia molecule again as an example. The electron geometry for electron groups, tetrahedral. And the angle here is perfectly 109.5 degrees. However, in ammonia molecule, there is a lone pair. The molecular geometry is not tetrahedral anymore, as we already discussed in previous slides. So the molecular geometry is trigonal pyramidal. And the bond angle is smaller than 109.5 degrees. That's because of the effect of the lone pair. The larger the number of lone pairs, the greater the effect. So here there's 1 lone pair electrons in ammonia molecule. Therefore, this bond angle is 107 degrees. But with 2 lone pairs, like in water molecule, they squeeze the bonds even more. Therefore, in a water molecule, the bond angle is 104.5 degrees. That's why we say the larger the number of lone pairs, the greater the effect. The relative size of repulsive force interaction follows this trend. Lone pair is greater than lone pair bonding pair, and that is greater than bonding pair interactions. We know in multiple bonds there are more electrons shared between 2 atoms. Because of that, the electron repulsion is stronger than that in single bonds. Therefore, in this formaldehyde molecule, the bond angle in an ideal trigonal planar shaped molecule should be 120, 120, and 120 degrees. However, because of this double bond, there are more electrons here. The electron repulsion is greater than those single bonds. That's why those greater number of electrons, bonding electrons, pushed those bonding electrons a little bit away from this oxygen atom. As a result of that, this hydrogen-carbon-hydrogen bond angle is much smaller than 120 degrees, and those 2 bond angles are increased to 129, 121.9 degrees. That's the effect of multiple bonds on bond angles. Now let's predict the molecular geometry and bond angle in acetic acid. So this one is a larger molecule with more than 1 central atoms. In this case, we need to assign geometry about each of the 3 central atoms separately. So those are the three central atoms. Carbon 1, carbon 2, and 1 oxygen right here. Let's work on the first carbon first. There are 4 bonding groups and no lone pair. Therefore, the molecular geometry has to be tetrahedral, and the bond angle is about 109.5 degrees. The second carbon, there are 3 electron groups. Please recall, double bond is counted as just 1 electron group. If it's 3, then the molecular geometry, no lone pair, then the molecular geometry is trigonoplanar. The bond angle should be approximately 120 degrees. However, if we take a closer look in this acetic acid molecule, because of this double bond, this bond angle, carbon-carbon oxygen, and this bond angle, oxygen-carbon oxygen, they are greater than 120 degrees. Because of their stronger electron repulsion, this carbon-carbon oxygen bond angle is smaller than the standard 120 degrees. Now, the oxygen atom, central atom. This oxygen is not a central atom. It's a surrounding atom. For this oxygen atom, there are 2 lone pairs and 2 bonding pairs. The electron geometry is tetrahedral, but the molecular geometry should be just bent. And the bond angle is less than 109.5 degrees because of the impact of the 2 lone pairs. That's not shown here, but it's shown in here. That's it for lecture 45. If this material is helpful, please subscribe to this channel and forward the link of this channel to your friends who are also studying chemistry. I will see you guys in lecture 46, bond polarity and molecular polarity.